Then we will start. Hmm. So our resource person has joined. Hello everyone, welcome to all of you. A very hearty welcome to our speaker, Dr. Mukesh Ujha sir. We are delighted to have your presence in our STC. Thank you for providing your valuable time for this STC. I am going to introduce about our resource person. Dr. Mukesh Kumar Ojha is currently working as an associate professor and head of the department in electronics and communication engineering at Greater Noida Institute of Technology, Greater Noida. He is having more than 17 years of experience in academics in various engineering colleges and universities. He received a PhD in signal processing from BIT Misr Ranchi main campus in the year 2020. He did ME in communication system from the Department of Electronics and Communication Engineering, Anna University, Chennai in the year 2007. His research interests include signal processing, machine learning, blind source separation, pattern recognition, and its application towards brain-computer interface and Internet of Things. He has published several limited national and international papers in SCI Scopus Journal and attended various separate conferences. He has also chaired in many national and international conferences. He is also an active member of various technical communities such as IEEE, Institution of Engineers India, and IIT India. I welcome, sir. I would like to request our speaker to deliver his talk. Hand it over to you, sir.
Thank you, sir. Am I audible?
Yes, sir. You are audible.
Thank you, sir, for nice introduction and giving this opportunity to me.
Little bit voice is slow, sir. I think.
Now, am I audible, sir?
Yes, sir. Yes, sir.
Yes. So, thank you once again, sir, for providing this opportunity to me. Uh, a second. Now, screen is visible to all of you.
No, sir. Screen is not
एक
visible.
second. Please wait for a second, sir. Hmm. Oh, God, yeah. I think some problem I am getting in sharing the screen. So, please hold for a second, sir.
Sir, just click on arrow button.
I have clicked. Sir. Yes, sir, I have clicked.
Click on arrow button and share entire screen.
Same thing I'm doing, sir. Yes. Now I think it's visible, sir.
Yes, sir. Visible, sir. Visible.
Okay. Am I audible to all of you?
Yes, sir.
Yes, sir.
Yeah, so good afternoon to one and all. Here I am going to give the presentation on signal processing approach for brain-computer interface. Myself, Dr. Mukesh Kumar Ojha, Associate Professor, Department of Electronics and Communication Engineering, Greater Noida Institute of Technology, Greater Noida. These are the outlines of my talk. Introduction to brain-computer interface, various paradigm of BCI system, introduction on SSVEP-based BCI system, detection of SSVEP component from the single-channel EEG signal based on EMD technique, detection of SSVEP component from the single-channel EEG signal based on discrete wavelet transform, and the detection of SSVP frequency component from the multi-channel EEG signal based on BSS-CCA algorithms. So I will start my talk with the introduction of
Voice is not audible, sir. Screen is stuck. Not audible. Why is not audible, sir?
Am I audible now?
Yeah, audible, but little bit coming slow, gradual.
Okay,
Not
and
audible.
my screen is shared with you or not?
Not screen is here. Sir, you just put off your camera. Maybe
Yeah.
due to that, yeah, data is taking more, no? If you are running through mobile, then I think this is the problem.
एक second. Now it's visible, sir.
Yes, sir.
Okay.
Can and if sir, I think you if put off your camera, then it will be run smooth. It
Okay.
will conduct smooth. Maybe
Okay.
data is consuming more. That's the problem. Okay, sir. Please
Okay.
proceed.
Okay. Am I audible to all now?
Yeah, audible, audible.
Yeah. So these are the outlines of my talk. Introduction to brain-computer interface, various paradigm of BCI system, and then introduction on SSBEP-based BCI system, then the detection of SSBEP frequency component from the single-channel EEG signal based on EMD approach, then the detection of SSBEP frequency component from the single-channel EEG signals based on discrete wavelet transform approach, detection of SSBP frequency component from the multi-channel EEG signal based on BSS CCA approach. So I will start my talk from introduction on the BCI. A research on BCI began in 1970s at the University of California in Los Angeles under a grant from the National Science Foundation. And the definition of the brain-computer interface is given as a direct communication between the thought of the human and a machine via computer without involving any muscles of our body parts. Uh, this is a complete block diagram for any BCS system. Here we are going to put number of sensor on the scale of the brain to record the brain signal, and this data is going to be recorded within a data acquisition system where we are going to amplify the signals, and also we are going to convert this analog signal in the digital form. Finally, this recorded signals is going to pass through this pre-processing block, and the function of this pre-processing is to minimize the noise, to minimize the artifacts, which is associated with the recorded EEG signals. Then this pre-processed signals is passed through some various feature extraction technique, and the purpose of this feature extraction method to extract various features from the pre-processed EEG signals, and finally translate these features into a certain command to control some devices like moving a robot either right, left, backward, forward, moving a wheelchair either forward, backward, right, left. So this too is the block where signal processing approach is going to play a bigger role. One in terms of minimizing the artifacts or noise from the recorded ESG signal, and then second one is of extracting the features from the pre-processed EEG signals. Now I am audible to all. Hello.
Yes.
Yes, sir.
Okay, right. So this is how we are going to identify the brain pattern. So recorded brain signals is known as EEG signals. This signal we are going to pass through various filter circuit, and the purpose of the filter circuit is to minimize the artifacts, to minimize the noise that occurs because of various parameters like eye blinking, movement of our body parts, various artifacts are going to be generated. And in general, in the BCI system, we are using the filtering technique. One as the frequency filtering, like FIR filter, IIR filter, and some advanced level of the filtering, like EMD approach, wavelet decomposition approach, just to minimize the artifacts. And then here we are applying various algorithms to extract the feature from the specific band of the brain signals. And then the extracted feature is going to translate as a command. And if I want to measure the performance of the system, here we are using various classifiers just to find the accuracy of the system, or other parameters like how to find the transmission rate, what is the rate of transmission, and how to minimize the time complexity of the system. So the performance parameter is going to find out by means of classifier, and in general we are using the linear classifier here. But in today's talk, I'm going to discuss in details about the various feature extraction method and what the pre-processing technique we are going to apply in order to optimize the performance of the system. So this is the way to measure the brain signals from the scale. A standard methods we are using. This method is known as 10-20 electrode placement system. The meaning of this 10-20 electrode placement system is that if I'm going to put one sensor at this point and another sensor if I'm going to put at this point on the scale of the brain, the gap between this should be 20 mm. 20 mm. Similarly, if I am going to put another sensor here, this gap should be maintained as 20 mm gap. And some of the electrodes we are going to put for the reference purpose. So the electrode which we are going to put for the reference purpose, that should be 10 mm away from this location. That's why this name is given as 10-20 electrode placement system for recording the EEG signals. And within this brain structure, this front area is known as frontal lobe. Second one is known as parietal lobe, and third one is known as temporal lobe. And last one is, which is in the backside of our brain. This is known as occipital region or occipital lobes. Depends upon our brain activities, these lobes are going to be prominent. If I'm talking about if I'm doing some mathematical calculation, reasoning calculation, more, if I want to control some devices, so that time the brain activity is going to be more strongly appear in this region, frontal region. Similarly, if I'm going to focus on some visual stimulus that is going to flicker in front of your eyes, then there is a strong response occurs in this occipital region of the brain. Anyone have the question here? Now we can classify the brain signals based on the frequency band, and in general, the brain signal is classified into the 5 band. One is known as alpha band, another one is known as beta band, third one is known as gamma band, then theta and delta band. In general, once we are in a very relaxed condition, the neurons which is going to occur within the brain, they are activate within the brain. Their frequency range is within this 88 to 14 hertz. And when we are in the very conscious state, that time the neurons are going to be activated within the frequency range of 14 to 30 hertz. And similarly, once we are in a very deep and unconscious state, the frequency is very slow frequency. Neurons are going to activate with a very slow frequency. That band is known as your delta band. These are the main challenges once we are going to design any BCI system. One is the low information transmission rate. Second one is the processing time is very, very complex here. And naturally, the recorded signals amplitude is occurs in the microvolt. So the signal to noise ratio is very, very less. So these are the challenges associated with the BCI system, and still a lot of people are working in this domain to minimize this kind of the problem. There are various paradigms to design the BCI system. One is known as your P300 motor imagery, and similarly, another one is known as steady state visual evoke potential based BCI system. So, in today's talk, more or less, I'm going to discuss about the SSBEP based BCI system. So, what is SSBEP based BCI system? See, uh, if you see this pattern within this, we have the two box. One is flickering. One have the color of black color, another have white color. And since both are having the different colors, I mean to say both are going to flicker at different frequency. So if any user is going to focus on any one of these box, then a certain signals is going to generate in the occipital region of the brain, and that signals is known as steady state visual evoke potential. I will discuss here in the details in the. So if you see this SSBEP based BCI system completely, the user is going to, this is the user or subject, he is going to focus on this pattern, and this box have the different colors. One is of white, another of black. So when the user is going to focus on any one of these stimulus, there is a response generated on the back side of this brain, and that region is known as occipital region. And this response is going to generate in the form of sine wave. And if this is going to flicker at a frequency, a certain frequency, the signal which is going to generate here also contain the same frequency. This recorded signals is going to store within the data acquisition system. And then from this, we are going to apply this pre-processing technique and the feature extraction method just to find the performance of the system. So these two parts I'm going to discuss in much more details in the coming slides. So this kind of the BCI system is known as SSBEP based system, where once the user is going to focus on a stimulus, that stimulus is going to flicker at a certain frequency, then there is a response generated within the certain region of the brain. That region is known as occipital region. From that region, we are going to extract this frequency component. And finally, we are using this frequency component to control some device. These are the evaluation parameter for SSBP based BCS system. And still, there are many researchers working on all these three parameters. My work is mostly related with this classification accuracy and the information transmission rate. So more or less, I'm going to find out the accuracy of SSBP component from the recorded EEG signals. To do the processing, I have taken the two data set. One is of the single channel data set and another one is of multi-channel data set. This multi-channel data set were the recorded signals in the Riken Lab, Japan, from where I got this data, and I have worked on this data set. And on this single channel, we have already recorded in our lab at BIT Mesra. And on this, I have applied the two techniques to find the accuracy of the system. One is called EMD-based power spectrum density analysis. And the second one is the discrete wavelet transform power spectrum density analysis. This EMD and DWT I have used as a pre-processing technique, and power spectrum density analysis I have used as a feature extraction. And then finally, I have compare these two methods just to find out which one is more suitable for basically for the EEG signal, which is non-stationary, which is non-linear in the nature. And for this multi-channel data analysis, one of the popular method we are using in the BCI, that is known as canonical correlation analysis for the feature extraction, and for the pre-processing, I have used first time here as a blind source separation method. So this is all about the description of the single channel SSVP data set. The signal was recorded at the sampling rate of 5.2 hertz, and the distance between system or computer and IA was around 60 centimeter. Uh, and the frequency at which the stimulus was flickering was 10 hertz, 6.5 hertz, 6 hertz, 7.5 hertz, 7 hertz, 8.2, and 9.3 hertz. So this is the layout of our setup. This is one stimulus which is flickering at 6 hertz. This is the another stimulus which is flickering at 6.5 hertz, and the gap between these two is 1.8 centimeter we maintain, and vertically we maintain this gap as 2.1 centimeter. And here this is 10 to 20 electrode placement system. We have put our sensor on the OZ location. This location, why we have chosen? Because SSVP signals are more prominent and at this location. This generally occurs in the occipital region. So we placed our one sensor on the occipital region of the brain, and another for the reference purpose we have put on our ear, so that to find the potential difference between these two. And here on this monitor system, we have recorded the signals. This is the uh, one EEG data recorded, which when the user is going to focus at the frequency of 10 hertz. So this is the recorded signals, and I have shown here this as a normalized value between +1 to -1. So this signals is recorded when the user is focused on the stimulus, and that stimulus is going to flicker at 10 hertz of the frequency. So this is not the SSBP signal. This is our recorded EEG signal. From these signals, we have to find out a frequency component of 10 hertz. And mainly, this 10 hertz frequency is going to apply as a command to control some device. For example, if I am going to choose this 6 hertz of the frequency, 7 hertz, 10 hertz, and 8 hertz of the frequency, one frequency is going to give one command to the device. Another frequency, we are giving the another command to the device. For example, if I want to move a robot right, left, forward, backward, I can use this 10 hertz frequency as a command to move the robot on the right side. I can use this 6 hertz of the frequency as a command to move the robot on the left side. I can use this 9 hertz of the frequency to move the robot backward side, and I can use this 7 hertz of the frequency as a command to move the robot forward. So this is the basic intention of the work, how to control some device using this frequency component. This was the method I have applied to extract this frequency component from the recorded EEG signal. So in
Why he not audible, sir?
Am I audible now? Hello.
Yes,
Yes,
sir.
sir, you are audible, but screen is no, PPT is not visible.
I'm sorry, I'm getting some problem with the network here.
Yes, yes.
Now it's visible, sir.
Yes, sir, yes, sir. Please proceed, sir.
And I have to start from this slide, or I have to go back side.
You may start from here itself.
This one.
Sir, till where you have finished, just start from there. Not a problem, sir.
Okay. So I was discussing about this SSVP based BCI system. Shall I start from here?
Yes, sir, start.
Yeah. So this is a complete block diagram for any BCI SSVP based BCI system. Here, one subject is going to focus on a pattern, and within this pattern, we have the two box. One is of black, another is of white box. Once the user is going to focus on any one, this box is going to flicker at a certain frequency. Every color have the different amount of the frequency. So when the user is going to focus on any of this box, a strong response occurs on the back side of this brain. This region is known as occipital region. Signals which is recorded in this region is in the sinusoidal form, and the frequency of that signals is same as the stimulus frequency, which is going to flicker at the certain frequency. Finally, this recorded signals is going to store in a data acquisition system where we are going to amplify the signals and we are going to convert the signals in the digital form. Yes. And from this recorded signals, we are going to minimize the artifacts and the noise by using various pre-processing technique. Then from the pre-processed signals, we are going to extract the features, and these features we are going to control. We are going to use as a command to control some devices here. So recently, the people who is working in this domain, they are basically work on these three parameters. One is of classification accuracy, another one of information transmission rate, and another is on the computational time. In this talk, I'm going to I'm going to more focus on this classification accuracy of extracting the SSBEP frequency component from the recorded EEG signals. So basically, in my work, I have worked on the two data set. One is of single channel EEG recorded data set, and another one is of the multi-channel data set. This multi-channel data set I have taken from the Riken Lab, Japan. And I have applied algorithms to find the accuracy as blind source separation CCA approach. CCA is one of the most widely used approach to extract the feature in SSBEP based BCI system. For this single channel SSBEP dataset, I have applied pre-processing as EMD technique, and second one pre-processing as discrete wavelet transform technique. And then to extract the feature extraction technique we have applied here is the power spectrum density analysis using Fourier transform. So EMD and DWT is basically applied for the pre-processing of the signals, and the PSD means these are the features we are going to extract from the pre-processed signal using FFT approach. So this is the description about the single channel data set. The data was recorded at the sampling frequency of 5.2 hertz, and the distance between the eye and the system was maintained as 60 centimeter apart from each other. The stimulus frequency we are using here as 10 hertz, 6.5 hertz, 6 hertz, 7.5, 7, 8.2, and 9.3 hertz. This is the complete setup, and we recorded the signals in the EC department, BIT Mesra Ranchi. Uh, if you see this layout, we have this is one stimulus, this is another stimulus. This stimulus is flickering at 6 hertz. This is going to flicker at 6.5 hertz, and the distance between these two is 1.8 centimeter. Vertical distance we have maintained as 2.1 centimeter. And to record this, once the user is going to focus on this stimulus, same frequency response of the signals is going to generate on the occipital region of the brain. And how we are going to do the recording? Here we put one, this location is known as OZ, and this is mainly within this occipital region. One sensor we have put at this location on the scalp of the brain, and for the reference purpose, we have put one sensor here near to our eye ears, so that to find the potential difference between that two. And here on this monitor, we are going to record the signals. So this is the recorded EEG signals, and this signals is recorded when the user is going to focus on this stimulus, which is flickering at the frequency of 10 hertz. The objective is to, this is not my SSBEP signals. This is the EEG signals. This is the recorded EEG signals. The objective is to extract this frequency component 10 hertz from this recorded signals. And why we are going to extract this frequency component? Because suppose if I am going to extract this 6 hertz of the frequency, this 6 hertz of the frequency we are using as a command to control some device. This 6.5 also we are using to control some device. But I mean to say, this one we are using as a command to control the device. So if I am going to, for example, if I have to control a robot, I want to move a robot on the right side. I want to move a robot on the left side. If I want to move the robot on backward or forward side, this 6 hertz of the frequency we can use to move the robot, right? This 6.5 hertz of the frequency we can use as a command to move the robot left side. This 10 hertz of the frequency we can use as a command to move the robot forward. And this 8 hertz of the frequency we can use to move the robot backward side. This is the purpose. That's why we are going to extract this frequency component from the recorded EEG signals. This is the method I have applied to extract the frequency component. The recorded signals first we normalize between +1 to -1. Then I have applied empirical mode decomposition as a pre-processing technique. And since the signals are non-stationary, non-linear in nature, we have to segment in the signals in number of segments just to make it stationary signals. And on each segment, we are going to apply the FFT approach to calculate the power spectrum density as a features. And if the peak of the power spectrum, which occurs at the given frequency, is above this threshold value, then we are going to use that segment as a true segment, else we are going to use that segment as a false segment. So, empirical mode decomposition is one of the advanced signal processing approach, and this one mainly applicable once the signals are nonlinear, non-stationary in nature. In this EMD approach, we are going to decompose the signals in number of oscillating components, and each component is known as intrinsic mode function IMF. These are the steps to find the IMF component. First, we are going to find the maxima and minima of the recorded EEG signals. Then we are going to calculate the mean value by finding the upper envelope and the lower envelope. And then we are going to extract this oscillating component by means of x of t minus m of t, where x of t is the recorded EEG signal and m of t is the mean value. So this 5 to 6 step we have to follow just to justify that given oscillating component is the IMF or not. The basic idea for this technique is partial signal reconstruction by appropriate selection of IMF and the exclusion of those IMF that contribute the noise contamination of the signal. I mean to say, we are going to decompose the signals in number of oscillating components, but only we are going to choose the components where my desired signals is going to be more prominent. For example, if I want to extract the 10 hertz of the frequency, only we are going to choose that oscillating component where 10 hertz of the frequency is going to be prominent. And how the selection is done? Selection is done by means of power spectrum density analysis approach, where we are going to find out the amplitude of the signals at a particular frequency. So if I'm going to get signals of the highest peak value at a given frequency of the 10 hertz, which is my desired frequency, then I am going to choose that IMF, and others we are going to discard here. So 10 hertz here we have decomposed that 10 hertz frequency of the recorded EEG signals in number of IMF, IMF1, IMF2, IMF3 like this. And then on every IMF, on every this oscillating components, I have applied the FFT approach to calculate the power spectrum density. So let us see. Once I calculated the power spectrum density of the first IMF, I am getting a peak value at the frequency of 30 hertz. This 30 hertz is nothing but the harmonics of the fundamental frequency 10 hertz. Similarly, if I am seeing this IMF2, this second oscillating band, here we are getting a peak value at 10 hertz and another peak at 20 hertz. This 20 is nothing but the harmonics of this 10 hertz frequency. And you know that recorded signals was recorded when the stimulus was flickering at 10 hertz of the frequency. So the recorded signals contain an informative signals of frequency 10 hertz. So objective is to extract the oscillating component where 10 hertz frequency of the signals is going to be more prominent. So based on there, that we are going to do the selection of IMF. So in our case, if you see this diagram, IMF1 contain the 10 hertz frequency, IMF2 also, and this IMF3. The rest of these oscillating components contain more amount of the noise. So first part is to dismantle all this noise component and get back only the oscillating component in which the 10 hertz frequency is going to be prominent. So after doing this process, we have assembled these three IMF1, IMF2, and IMF3. Convert the signals in the time domain analysis, and then we are going to do the power spectrum calculation. So from IMF, I have chosen this IMF 1, 2, and 3, and then I segmented that signals into number of segments, each of the 2 seconds. And within this, we are going to see which segment contain the peak value at 10 hertz. So this is going to contain, like this we have to proceed. So the segment which in which the 10 hertz frequency is prominent, that segment we are using here as a true segment, and where 10 hertz of the frequency is not in the prominent stage, that one we are going to use as a false segment. And then the accuracy we are going to calculate by means of the true segment upon total number of segments. So this is the result I got for subject 1. For once the stimulus is flickering at the frequency of 6 hertz, next time it is going to flicker once the user is going to focus on a frequency of 6.5 hertz. So I compare this with this. Here directly we are going to calculate the power spectrum density on the raw EEG signal without applying any pre-processing technique. And once I applied the empirical mode decomposition as the pre-processing technique, and then I calculated the power spectrum density, I achieved this accuracy 84.40. So overall, for one subject, if I'm going to apply the EMD as a process technique, the overall average accuracy I achieve as 87.30. And if I'm going to calculate the power spectrum density from the raw EEG signals, that in that case, accuracy I achieved as 85.40. So by means of this conventional method, the accuracy is 85.40. And once if I'm going to apply the pre-processing as EMD, accuracy is slightly going to be improved by 2%. It is coming around 87.30. So in the same way, we have the 4 subject. For 4 subject, I did the analysis and I calculated this value. And then the second one, I compare this EMD approach with the discrete wavelet transform approach, and where I have justified that EMD is more powerful once we are going to deal with a non-stationary non-linear signals as compared to the discrete wavelet transform. And that's why people who is working on the pre-processing area in the BCI system, now most of them is going to either use the empirical mode decomposition as a pre-processing or multi-mode empirical mode decomposition as the pre-processing technique. That depends upon the nature of the data. Same approach I have done here. First I normalize, then I apply a frequency filter, FIR filter within the band of frequency 4 hertz to 16 hertz. Then I decompose the filtered signals, one by means of the discrete wavelet transform, another by means of the EMD. In the DWT, we are going to decompose the signals in the number of subbands, and from this subband, we are going to choose the subband where our desired frequency component is more prominent. And then I compare the result of these two. So wavelet transform, we are using a window, and that window is always sliding in nature, not a fixed window. And just we are going to segment our recorded signals in number of segments by means of the windowing technique. And here signals are going to decompose not in the oscillating component, it is going to decompose in the number of subbands. And this approach is going to provide what the frequency component exists at what time of the interval, which is missing with the Fourier transform. And if I'm talking about the short time Fourier transform. So this is the general equation for any mother wavelet, continuous wavelet transform. This is already theoretical part. Here I will focus. In DWT, we are using a filter bank approach to decompose the signals in number of subbands. In this approach, we are using the two filters, one as high pass filter and low pass filter. The recorded signals is going to apply to this filter, high pass and low pass filter. And finally, the output of this high pass filter, since we are not interested to get the high pass filter output, this one is going to be discarded. because the message or information always take place in the low frequency range. So we are going to choose the output of the low pass filter, and then we are going to use these signals again for the next stage and for the another stage. In every stage, this is the way the decomposition of the signals take place. Signals which we have recorded was at the frequency of 512. Sampling frequency of that signal was 512 hertz. So maximum frequency of the signal is nothing but the sampling frequency upon 2. So first in the first stage it is going to decompose from the 256 to 128. In the second subband, the frequency is will be in the range of 128 hertz to 64 hertz. In third subband, it is from the 64 to 32, and 32 to 16. This band is known as beta band. In alpha, we have 16 hertz to 8 hertz frequency. And you know that all the stimulus frequency was within this range. One was flickering at 6 hertz, another one was flickering at 6.8 hertz, 5 hertz. The last one was flickering frequency was 10 hertz. So all my desired frequency component is going to be within this band. So objective is to discard this kind of the band and only do the analysis on this band of the frequency component. So in our work, what I have done, I discarded all this subband of the frequency, and only I have chosen this band. And sometimes some of the frequency component may be appear in next band also. So only I have chosen this and this band. Then I applied the inverse discrete wavelet transform approach to convert the signal from the frequency domain to the time domain. And then I segmented again a number of segments. And on every segment of, hello, am I audible? Hello.
Yes, sir, audible, sir,
Yes.
audible.
So only I have chosen this band, 8 hertz to 16 hertz band and 16 hertz to 32 hertz of the band to do the further processing. So this is the way we have decomposed our 10 hertz of the signals, which was recorded by using by placing only single electrodes on the scalp of the brain. I have decomposed this, and from this, only I have chosen this band D5 and D4. D5 and D4. These two band I have chosen for the further analysis. Rest one is the noise for me only. So no need to go with the analysis of D1, D2, D3 band, D6 band, D8 band, D7 band. And then again, I convert that from the frequency domain to the time domain. And again, I segmented the signals in number of segments. For example, if the signal exists for the 30-second, I segmented everyone in the 2 second, 2 second, or 1 second, 1 second range. So this is the segment. This is another segment. This is another segment. And again, I have applied the FFT approach to calculate the power spectrum. Sir, am I audible now? Hello.
Yes, sir.
And the slide is visible to all of you?
Yes, sir.
Okay. So I'm sorry, I'm somewhat getting the network issue here. Shall I start from here or I have to go to the back slide also?
You just start from here only, sir, because you are
Yes.
having just 25 minutes.
Okay. So this is the result I have got. If you see, this segment within this segment, the maximum amplitude of the signals I am getting. The maximum amplitude of the signals I am getting at this frequency 10 hertz. Similarly, in this segment also I am getting a 10 hertz. Maximum amplitude at the 10 hertz. So this segment is known as the true segment. But if I am going to see this one, here at 10 hertz frequency is not, at 10 hertz frequency, we are not getting a maximum amplitude of the signals. So this segment is not the true segment. So once I'm going to calculate the accuracy of the system, we are going to use the how many number of true segments we have got divided by total number of segments. That will give you the accuracy of the system. This is the result I obtained by using the EMD, and this one I obtained by means of your DWT. DWT. And finally, here I compare the result. Then I got, once if I'm going to apply the EMD and PSDA combined approach, the accuracy was 91.66%. And by means of discrete wavelet transform and power spectrum density analysis, the accuracy was 88.88%. And simply, if I'm going to apply the power spectrum density on the raw EEG signals, that is known as the conventional approach, the accuracy was 84.70%. So I can say, based on this result, EMD is going to perform more for non-stationary, non-linear signal as compared to the DWT approach. And the reason is, if you see the wave form or the pattern of the EEG signals, it is more likely to be empirical as compared to the linear. And that's why EMD is performing more as compared to the DWT approach. This is the result I got for all the subject, and I compare this. Then the second data set is the multi-channel data set. This data set, this is the offline data set. I worked on this data set, which was recorded in the Riken Lab, Japan. Total number of channels we here they have used to record is 128, and the length of every recording is 15 seconds. The total number of trials was 60, and total number of subject was 4. Out of this 128 channels, only I have chosen the channels which is placed on the occipital region of the brain. And this is the stimulus. They are flickering at the frequency of 8 hertz, 14 hertz, 28 hertz. And these are the channels location we have chosen. And these channels are placed near to the occipital region. Total number of 8 channel selection we have done. And this is our approach to find the accuracy. First, I apply a band pass FIR filter on the recorded EEG signal to get the filtered signals. Then I prepare the new data set. And then here Blend source separation as a pre-processing technique we have applied to minimize the artifacts or to minimize the noise. And then after pre-processing of the signals, we have chosen canonical correlation analysis approach to extract the feature from the pre-processed signal. And then in CCA approach, we are going to find the correlation coefficient. Maximum correlation coefficient is considered here as a SSBP frequency. Am I audible? Hello.
Yes, sir, audible, sir.
Yes. So I will not take much more time about the BSS approach. Here, basically, this is called the sensor signals. This is our recorded signals. Once I'm going to put the number of sensor on the scale of the brain. This is the source signals, means this signals is going to generated by means of the neurons. And this is the noise which is contaminated along with the source signals. So in our case, in general, if I'm talking about the recorded signals, means this is our EEG signal, and this S1 and S2 and SM is nothing but our SSBP signals. So here we are using one technique that is nothing but called independent component analysis. By means of this ICA technique, we are going to separate the source signals from this noise signals. So recorded signals contain your informative signal as a SSBP signals, and other EEG component which is going to occur from the backside, that is known as the noise signal. And the purpose of this demixing system is to separate the source from the noise. And this is done by means of one approach known as a blind source separation method. Here there are n number of methods. One method we are using as a MU's algorithms, which is quite simple as compared to other methods. So these are the mathematical approach how we are going to separate the source from the recorded mixed signals. So this whole process is done in the 3 step. First, we are going to calculate the covariance matrix. Then we are going to apply the eigenvalue decomposition to get the clean signal. And then we are going to separate the signals using the ICA approach. So this is our mixed signals. This is the whitened signals. And then here we are going to separate the signal 1 and signal 2. CCA is one of the most widely used approach in the SSBEP based BCI system, and by means of this correlation, canonical correlation analysis approach, we are extracting the features. So in CCA, what we are going to do, we are going to compare the two signals. One is the recorded signal, and same kind of the signals we are going to use as a reference signal. For example, if I'm going to record the SSPEP signals, the nature of the signals is just like sinusoidal wave, having the frequency of 10 hertz or 6 hertz that depends upon the stimulus frequency. So same kind of the signals, either sine and cosine of the 10 hertz frequency, we are going to generate as a reference signals. And then we are going to find the correlation between that two. If the correlation coefficient we are getting at that frequency as a maximum value, then this maximum correlation coefficient is taken as one SSBP frequency component here. So this is the approach we have applied here. This is the recorded signal. In the pre-processing stage, I have applied the MU's algorithm as BSS technique. Then we are going to discard the noise from the source signals, and then this source signals is going to apply to the CCA technique. And on another input, we have the reference signal as a sine or cosine signals having the same frequency as the stimulus signal frequency. And then we are going to obtain here in the output of the CCA is the correlation coefficient. If the correlation coefficient have the maximum value, then this is known as a stimulus frequency. So again, this is the mathematical calculation we have to do. We have done. And once we are going to do the analysis of for multi-channel SSVP signals, not only the signal processing is going to play a major role, there are other factors also. Here we are going to consider the number of harmonics also. Here we are going to consider the selection of number of channels also. Based on that, I applied one for number of harmonics. I have taken 1, 2, 3, and 4. For example, if the fundamental frequency of the recorded signal is 10 hertz, first harmonic is 20, second harmonic is 30 hertz. Then I simply applied the CCA technique on the recorded EEG signals. And for 1 second, 2 second, 3 second, and 4 second of the segments, I obtained this result. And once I applied the blend source separation, here I have applied the MU's algorithms as a pre-process technique. And then I applied the CCA technique, I obtained this result. And here, these are the location from where we have placed the sensors. So only we have chosen the sensors, which is located on the occipital region of the brain. So 8 channels I have done chosen for the analysis of the signals. Then in another experiment, I have varied the number of channels. If I am going to select 8 number of channels, if I am going to choose 6 number of channels, and if I am going to choose the number of channel as 4, all are within the occipital region. Then I obtained this result in all the cases. So once we are going to calculate the accuracy, not only the signal processing method is going to play the role, also there are many factors like how many number of channels we are going to choose for the analysis purpose, how many number of harmonics we are going to choose, and also what is the segment length, whether it is of 1 segment, 1 second, 2 second, 3 second, or 4 segment, as 4 second, you'll get the different results. So in all the case here, I got the accuracy as 71.66%. So this is the final accuracy. Am I audible? Hello? Hello?
Yes, sir, you are audible, sir.
Yes.
Yes, sir, audible.
So this is if the window length is 1 second, yani ki one segment length is 1 second, this one the accuracy, this was the accuracy we achieved. And if the segment length is of 4 seconds, this much amount of the accuracy I achieved by simply by applying the CCA, and another by means of BSS and CCA approach. The same calculation I have done for 4 number of subject here. And finally, in the proposed method, we achieved the accuracy at 96.87%. While if I am going to apply the CCA approach directly on the recorded signals, the accuracy was 91.87%. So this is all about today's talk. This is the summary. The multi-channel raw EEG signals are correlated. The detection accuracy for multi-channel dataset is affected by mixing of actual source signals at each sensor point. Keeping in mind this proposed the BSS technique to decorrelate the sensor signals. MU's algorithm is chosen for decorrelation of sensor signals. And these are the conclusion. EMD power spectrum density commonly is going to be more effective as compared to the DWT and PSA approach for single channel. And in the multi-channel, we have simply applied the MU's algorithms. There are many higher order ICA techniques are available. which is possible to apply on the SSBP dataset also. Real time, we are working still on the real time, doing some projects or how to implement our algo on the real time analysis. These are the publication. First two, one is published in the 2SCI. One was published in year 2021. Another one also 2021. And third paper, which I have worked on BSS-CCA technique, is already accepted, and it is under the final revision. That's all from my end. If anyone have any question, they can put up the question. Yes.
Anyone question? Please, if you have any question, ask him, sir.
Sir, how to extract a feature? Is there only one way to extract the feature, sir, or the correlation matrix?
There are many way. Basically, the feature extraction, either it depends upon you, whether you are going to extract the feature in the frequency domain or you are going to extract the feature in the time domain. So for since here my job was to extract the frequency component, that's why I applied the power spectrum density as a feature. Yes.
And sir, what if I have seen there was one correlation
Yes,
matrix?
that is nothing but the canonical correlation analysis. This is not applicable for the single channel data set. Once we are going to record the signal from the multi-channel, one most popular method is the CCA approach. And in the CCA here, feature is nothing but your correlation coefficient.
Sir, what if the correlation coefficients of two such variable or features, whatever you have selected for analysis, are
Yes.
too high? So how we can eliminate one? Because if two features are highly correlated, we have to remove one. The
Uh,
variable, the variance inflation factor or something like that.
no,
So can
here
you comment on that, sir?
Here in the CCA, what we are doing, uh, actually, once we are going to do the recording of the SSBP signals, if you see the pattern of the signal, it is almost like sine wave or cosine wave, right? And that signal is going to contain the frequency which is equal to the stimulus frequency. First point. So objective is you in the CCA, what we are going to do, we are going to generate one artificial signals. That is nothing but the sine and cosine. And that one we are using as a reference signals. And finally, we are going to compare that signals with the recorded EEG or SSBP signals. And correlation coefficient is maximum, means both the frequency is going to match with each other. That's why that if correlation coefficient maximum value is taken here as that SSBP frequency. This is the concept in the CCA.
Okay, sir. So, is there any, sir, machine learning techniques you have applied for this analysis, sir?
Machine learning, I have applied the thresholding technique. Machine learning technique you can apply on the after the feature extraction. You can choose more number of features also. You take some mean value variance, right? And
Yeah, yeah.
then you make a pattern, and you can apply some algo like SVM. You apply KNN. You can compare the result. But my job was not on the classifier part. Actually, I
Mhm.
worked on the pre-processing stage and feature extraction part.
Okay, sir. I got it. Thank you so much.
Any question to anyone?
So, any questions? No questions. Okay, so thank you so much, sir, for
Sir,
taking time to share your experience with
Dilip
us.
sir,
Your lecture on the
hello.
signal processing strategy for the brain computer interface system was really educational. We learned about the PCI system from you. You informed us of the processes involved in recognizing the brain patterns as well as how to extract features from an double EG measurement device. You have proposed the challenges with BCI systems, how to tackle that, what is the methodology of recording double EG signal, the addition of case studies in your explanation definitely made it easy to understand them. You discussed how to use and extract features from the CCA-based BCI system, what is the linear relationship between the two-dimensional variable, and how does the application of BSA, CCA, and mathematical calculation enable the detection of SSBGP. In addition to the many practical experiments, data analog with its accuracy. I sincerely want to thank you once again more, sir, for your contribution to this STC. Thank you so much, sir. Thank you, Mukesh, sir. Voice is not audible. Your voice is not audible actually.
Sir, you are muted.
Oh, yes, yes.
Hello.
Yes, sir. Actually, what
Are
you
you
are
audible, sir?
Okay, sir. Thank you.
Thank you, Dilip sir, for giving this opportunity. And I'm really sorry for disturbance because of the network issue.
Yes, yes, sir. It may be conducted with anyone. It may be happens. So, of course,
And
we may not do
if
anything.
anyone interested to work on the BCI, I'm always ready to work along with them also in coming future.
Okay, sir. Thank you.
Thank you so much, sir.
Hmm. So, actually, I'm going to take you. Last session is my lecture, 3:20 to 4:30, and thereafter you are having what inaugural session from 4:40 onwards. So, in inaugural session, you have to give your feedback. So please prepare about each session. You have to means what you have liked, what you have disliked, what are your suggestions. You have to give it in inaugural lecture session, which is going to be conducted by 4:40 onwards. And we are also going to conduct Qs after my lecture. And of course, you just take break for 10 minutes. So I'm going to finish my lecture by only means 15 minutes before I will finish it. So okay, if you want to know about me, so currently I'm working as an assistant professor in the Department of Computer Science and Engineering, Triple IT Bhagalpur, since 9th May 2020. Before this, I have worked in the School of Computer Science and Engineering, Bangalore Institute of Technology, Bangalore, Tamil Nadu, from 13 May 2019 to 6 November 2020. I have also worked as an assistant professor in NIT Patna during 30 March 2017 to 9 May 2019. I have worked in also Bhopal in LNCT Oriental prior to 2014, from 2012 to 2014. So I received my PhD from BIT Mr. Ranchi in 2018. I received my MTech and BTech from RGPV University in 2012 and 10. I am the author of 2 books, one patent published, one copyright grant, and more than 67 research publications in a reputed international journal, chapter and conference proceedings. And I also received one project as a co-PI funded by TQ Collaborative Research Team. Currently, I am guiding 3 PhD research scholars and have guided many PG and EDU students. I have conducted many FDP short-term courses, delivered many expert talks in FDP workshop conferences, as well as attended. I reviewed many research papers in reputed journal conferences, edited book. I am the member of several professional bodies such as IEEE, IANG, ISO, SWIWC. My research areas are artificial intelligence, machine learning, deep learning, data science, soft computing, pattern recognition, bioinformatics, data mining, database management system, IoT, etc. So this is my mobile number. You may, if you want to know more, if you need more information, then you may contact in institute website or of course you may go in institute website, so you may check it. So today I'm going to present my presentation. So slide is visible.
Yes,
Yes,
sir.
sir. Yes, sir. Yes, sir.
Okay. So today I am going to present my title of presentation classification of diabetes disease. So these all are the contents for today's lecture: classification, motivation, dataset partitions by using Wika, classification technology, machine learning, short computing, data mining, feature selection, and okay. So these all are the things I'm going to discuss. So simple. We have already seen many lectures, 14, 15 lectures, and everybody have discussed about predictions and classification. So what is classification? The grouping together of similar things into different segments based on common qualities of attribute. But this is not the exact definition of classification. This may be also what? Clustering. This may be also called clustering. So what is the difference? Classification is a supervised learning method. And clustering unsupervised. Okay, classification is a supervised learning method. That is, the training data has to specify what is to be learned. Since a training set exists, this method is known as supervised learning. So this is clear in classification. Training set is going to be existed. It's training and testing. Okay, fine. So in classification, the data set we partition the database into training and testing. And generally we do it 70 and 30. But this is not hard and fast that we have to do it only in 70 and 30. It is dependent upon, means we have to just do hit and try. 60 40, 70 30, 80 20. This is just like I am telling you 70 30. If we are getting good road and if you are driving car, so you have to drive by only 80 speed. If you are driving bicycle 60. So this is just like we should start 70 and 30. And one term is also validation. If you want to improve the performance of training, so we go for what? Validation. So validation is but not compulsory part. So the training data set used to training the system and testing data set used to measure the performance of the system. Generally in classification, a set of predefined classes, and the goal is to find which a new object belongs to. So motivations. Why we do classification in medical diseases, just like here we have considered what? Diabetes. So it is well known that till some years back, physicians diagnosed the disease with experience and clinical data of the patient. By clinical data, you mean laboratory test report. So by laboratory test report, laboratory test. The laboratory test report depending upon meal, exercise, sickness, stress, due to small changes in temperature, different equipment used, and way of sample handling. So this kind of diagnosis of the disease is time consuming because it is entirely dependent on the reliability and the experience of the physician who has to deal with imprecise and uncertain clinical data of the patients. So to improve the decision making with clinical data and reduce time consumption, a good and intelligent diagnosis system is very much needed. Researchers said that even the most experienced of physicians is not capable enough to detect the disease quickly and accurately. He may require feedback from the several person for diagnosis of particular disease. It is always a problem for physicians to identify any disease accurately and in a speedy manner. The main problem behind any misdiagnosis of the disease are lack of communication. Patient does not communicate to the physicians well. This is the one problem. Lack of experience. Patient does not go to a well-experienced doctor. Lack of pathological report. Actually, pathological or laboratory tests are not available in small cities. It is available in only big metropolitan cities. So these all are the 3 points which are the problem behind any misdiagnosis of disease. So we have seen training, testing, and validation. We may see here in better what is the meaning of training. Training data set means to train a particular input so that later on we test them for unknown input. So training data set is used to construct or develop or learn model of classifier. The training data set is for training the system. What is testing? Testing data set is used to measure the performance of the system. Testing data set is used for assessing or to evaluate the model performance future data. Testing set is used to estimate future error rate. This is validation. I'm telling you that this is there is no hard and fast. We have to also split training, testing, and validation. Validation is optional part. If you are not getting the performance good in training, then we also partition validation to improve the performance of what training. Validation data set is used to check the quality of training, help to find the best combination of parameter. Validation data set is used to select a model based on summation of picking algorithm, no setting. The training, testing, and validation are used in intelligence system, machine learning, genetic programming. So how actually we may split training, testing, and in Python. Okay, just do command. We may do it in MATLAB also. This is available, but if you have to implement in some GUI, so you should have data, training, testing, validation. Yeah, all things should be in different places if you have to run it. So how you will split or partition the data set? This is the major question. Yeah, of course you may do it manually, but this is time taking and you may do mistake. So if Vika, I think maybe somebody have among you all have listened. So here option is to partition data into training, testing, and validation, and you may do it very easy in Vika, but in manually, I told you, okay, firstly the time is going to be taken more. Secondly, there is chance to do mistake. So how you may partition the data set in Vika? Firstly, I am going to you'll just see it, and then I'm going to do it in front of you because I want to give you some hands-on session by which you'll have means idea. Yeah, in this way I have to partition the data set, and of course practically you'll learn something. So okay, you may see here firstly. These all are the points. Start Vika, go to Explorer and click it. Click on Open File, go to Filter, choose Unsupervised, choose Instance, click on Read Sample, edit. I have just made it. Edit properties, no replacement sample size. Okay, apply. Undo revert. Click on Read Sample, invert selection. Two means you have to perform these many number of things. So I'm going to perform it in front of you once. So go in Vika, you have gone there, and then what you have to do? Go to Explorer. Yeah, this screen. Then what? Select the data set firstly. So where you have created the data set, you have to go there. Suppose we have taken diabetes dataset, famous dataset. This dataset has been obtained from shared repository or machine learning databases. P-Indian diabetes dataset. This is very famous dataset. We are going to discuss in very brief later. So you may see here 768 instances, and there are 9 features, including class. And you may see these all are the features, and these all are the instances. So how you may do it partition? How you may do it? You have to just go through here, choose. You have to go in filters, unsupervised, instance. Then you have to select what? Resample. Yeah, correct. You have to select resample. Okay. Then just click here and just do no replacement what? True. And If you want to split into what 60, I'm going to split all training, testing, and validation. If you want to do it, okay, go 60. You have done 60. Okay, fine. Then you have to do what? Okay, apply it. You have applied. Then just save it. Name train. Okay, save it train. Thereafter, you just go there, undo. Go in resample. You may see I am going to share the video recording. You may check it in that. Go there, resample, and then do invert selection. True. And just perform OK. Apply. Go in resample. Invert selection. False. And sample size 50. How many percentage? 40. 40 among 40 you are going to partition what? 50. Then do OK. Go apply. Save. If you want to do what? Validation. Okay. Then fine. Once again go undo. Then resample. Invert selection. Do it true. And then OK. Apply. Save. Paste. So only you may see it within 2 minutes. You may partition the data set into training, testing, and validation. If you want to look it, so go there. You may see you have partitioned it. So firstly you will check training. 460, okay, it's fine. Out of you have seen that 768 instances were there. Right now 460. 768, 60% is only 460. If you will go in what? Paste. This is 154. Fine. If you will go in validation, it will be also 154. Because among 40%, you have partitions what? 150, 50% validation and testing. I am also going to if you have partitioned some database, and with that, if you are once again trying to partition any database, you are going to get the wrong result. If you want to do, if I'm going to partition the same data set, you will see means simultaneously if I'm going to partition this data set, suppose in the same way, you are going to get the good result. So what you have to do, I'm telling because I'm not going to emphasize so much time on this. So you have to firstly close this. Yeah, this data set has been partitioned well. Firstly close this and then once again start from here. Explorer, go here. Then simultaneously you no need to perform the operation. Neither you are going to get the wrong result. So I told you that you go in. Suppose LDT. These were the real data set which I have collected in Ranchi, Bombay Medical Hall, Upper Bazaar, Ranchi. I have collected this data set. Okay. So 1058 instances is there. So and how many? 12. Somebody is I think online trying to. So okay. I told you that what? That 1058 instances there. These are the real data set. Okay. And if you want to what if you want to partition the database into training, testing, and validation, you have to go here, go to this instance. I told you select a resample. Go there, and I told you that what you have to do. You have to no replacement. You have to do it true and just do it 60. Okay. Apply. save, and name train. Okay, and then just do undo, click on resample, do invert selection true, okay, apply. Then once again go in resample, invert selection, false, and you have to partition among 40%, 50%. Do it, okay, apply, save. Suppose you want to do it, you may do anything, either test or validation. Suppose validation, you have done it, validation. Then once again I told you undo, go in sample, invert selection true, okay, apply, save, what, test. So you have partitioned the data set. Suppose if you want to see train LDD, so you may see out of 1058 C34 is 60%. Once again, if you want to go test LDD, this is 212. If you are going to check what you are going to get the same result. Okay. So right now, suppose I am train diabetes. Okay, 460. Because if you have, I told you that firstly you have to train the data set. So this is your training data set. How you have to partition, I told you. So those who are having a biological background, mathematics background, they are feeling a little bit here, I am not so much good in coding, yeah, or it will be taking time. So GUI comes in picture and it will help you. Okay, so only the problem of GUI, you may not tune the parameter, you may not change the parameter, and you may not modify the algorithm. Existed algorithm you have to use, but not any issues. If data set is novel, so of course, firstly you have to use only this algorithm. But if you want to modify the things, we are having the options. We have to use VK library. In NetBeans, you have to Java. You have to just import VK library, and you may do coding as per your own choice. But if you are directly using VK library, VK, so of course you are not going to get the option. But from other background, just like I told you, ki biological or some other. So this is very helpful. Okay, so I'm going to tell you. Okay, what do you just select this data set. I told you firstly because I am going to little bit give emphasis on new base and what decision. So I will firstly tell you new base. Just go there, select data set. Okay, so how you are going to select the data set? Here have you selected? Yeah. So okay, you have to apply. Just go start. You may see here. What is this? Precision, precision, recall, F measure, ROC, class. This is confusion matrix. Okay, these all are the terms. I'm going to discuss it. This is accuracy, kappa statistics, mean absolute error, root mean square error, relative. These all are the training performance. So okay, but these all are terms. Mean absolute, root mean, relative absolute, root relative. These all are basically famous in popular in where regression. But precision, recall, length measure, ROC, accuracy is generally considered in what classification. So, but we can give us all the parameter result. Yeah. So if you have to what evaluate the performance of the Nevis model for this data set. So just select it and select this data set, test data set. So we have test data. This is test. Open, close, select. So right now you may see 74%. You no need to tell get my 78%. Actually, training performance is always greater than testing performance. So your performance of the model is not 78%. Your performance of the model is only 74%. Okay, your model of the performance is only 74. If you are planning to use what decision tree, if you are planning to use decision tree, so what you have to do? You have to do here. Just go here, select once again. If you have, we want to perform on the same data set, so train diabetes. Okay, 468 instances. Go in classify. Here go and go in trees and select suppose J4. Not a problem. Right now your performance is what? 91%. Okay, you may see this is very good. Go in supply, select the test data set. Test diabetes. Okay, open, close. So right now, but you get only 70% in test one. Training performance was very good, but testing, when you test it, then performance is very down. This happens majorly. So we have to just partition the data set once again in different manner. We have to just perform 8 enter. So right now you may see, sir, how we will construct trees. Go there, simply conduct visualize tree. This is your tree. Go there, hit to tree. And right now you may what? Make the rule. You may construct the rule. Okay, you may write the rule. So this is all about what? Classification and okay. And if you have to perform feature selections, because I'm going to use this also term. So go train diabetes. Go here. If you have to use PCA, so go there, start. These four attributes are more relevant or significance among 8. So these all are the way, these all are the means what ways to perform data set in this tool. So this is very helpful if we are having, if we are little bit weak in what coding. So okay, so if we are weak or not, we should be aware for GUI, because in R also provide GUI Rattle package. If you are going to install, you may perform your task. In MATLAB, you also call all tools in GUI. Okay, so right now we are going to proceed further, and so my slide is, I think, visible. So in brief, I want to just tell you. Suppose I use the term sum. So firstly, I have used the terms because accuracy, what are important in classification. Accuracy, what is this? You know that, okay, sir. This is the ratio of number. This is the ratio of total number of correctly diagnosed cases to the total number of cases. Simply, sir, TP plus TN upon TP plus FN and plus TN plus FP. Okay, this is the formula. Okay, then precision. What is precision? Precision is simply key. So what is true positive? I have not told you. True positive is diabetic people correctly detected as diabetic people. What is true negative? Healthy people correctly detected as healthy people. What is false negative? Diabetic people incorrectly detected as healthy people. So what is false positive? Uh, what is false positive? Healthy people incorrectly detected as diabetic people. Okay. So and what is false negative? I told you that diabetic people incorrectly detected as healthy people. So these all are the terms. Once again I'm telling you, true positive means healthy people correct. True positive means diabetic people correctly treated as diabetic people. True negative means healthy people correctly treated as healthy people. False positive means healthy people incorrectly detected as diabetes people, and false negative means diabetic people incorrectly detected as healthy people. So what is precision? This is also called positive predictive value. This is the ratio of two positive to the sum of two positive and false positive. Okay. What is recall? Also called sensitivity to positive rate or hit rate. So precision two positive plus two positive plus false positive. Recall I told you okay, sensitivity. Recall is also called sensitivity to positive rate, hit rate. So two positive upon two positive, false negative. So this is specific. What is specificity? Is also called two negative rate, and specificity is only two negative upon false positive plus two negative. F measure is also called here in Wika we are telling F measure, but in Python simply F score. Okay, the F score is the calculated based on precision and recall. It is a trade-off between precision and recall, or it is the harmonic between precision and recall. Okay, so these all are the terms. Confusion matrix is also known as error matrix. It contains information regarding actual and predicted classification. So okay, we will discuss later because time will be finished only in this. So I am coming back in previous slide. So actually these all are terms very necessary. You must be aware to what perform any classification method. So we were here only. So we have just known how to partition the data set in Vika. Right now, what is classification? It may be, I have already told you, it may be defined as to finding the known target value based on the known target value in the data set. It enables us to retrieve a particular thing of information which is needed without too much time consuming. It helps us easier to organize things or easier to locate, retrieve, maintain things and information which make my life easier. Classification and regression problem are the example of supervised learning. There are several examples of classification problem. Classification of an email into spam or non-spam, prediction of cancer, gene classification into coding or non-coding, diabetic prediction, classification of transition and progenitor, many more. So many terminology are famous in what classification, just like classifier. What is classifier? Classifier is nothing but an algorithm that is used to make the input data specific. So naive Bayes, J48, DT perform, these all are the what? Classifier, classification model. The model predicts if you have implemented something and you told yeah this is the result, so becomes model. The model predict all DAs and complement to the input data given for training and it will predict the class or category of data. What is feature? Is also called as what? Attribute or variable. So is nothing but an individual measurable property of the phenomenon being observed. Binary classification means true. Okay, it is type of classification with two outcomes. It can either be true or false, one or zero, yes or no. Multi-class classification. The classification with more than two classes is known as multi-class classification. And in multi-class classification is simply assigned to one and only one level category. Okay. So multi-level classification, this is type of classification where each simply assigned to a set of level of target. So okay, fine. So working of classification. I told you training and testing. These both are going to be different. You are going to firstly apply ML on training, and thereafter you are going to perform on this and the performance of test data. What algorithm you are going to apply here? This is going to be become what means you are going to apply classifier. Suppose what you use here, you are going to use here only same, and you are going to get the result. So we always consider the test data result. So here you may see that same thing. So machine learning. What is machine learning? The term machine learning. What is machine learning? You will tell कि sir machine learning was first introduced by Arthur Shemoli in 1959. It is said as a subset of AI. So our FDP is title is what AI and IoT in biomedical engineering. So what is AI? You have to told कि sir artificial intelligence is made up of two terms, artificial and intelligence. What is AI? Artificial intelligence is made up of two words, artificial and intelligence. Artificial means man-made, intelligence means thinking power. So artificial intelligence means a man-made thinking power. Okay, what is the goal of AI? The goal of AI is to make a smarter computer like to solve a complex problem. Okay, to solve a complex problem. It leads to intelligence or wisdom. It leads to intelligence or wisdom. It will go for finding the optimal solution. Whereas in machine learning, it is a subset of what AI, which allows machines to learn from past data. Okay, and predict in present data and predict in present data. Okay, so what is the goal? The goal of ML is to allow machine to learn from data, so they can give accurate output. I told you that the AI leads to intelligence or wisdom, but ML leads to only what? It leads to simply knowledge. It leads to knowledge, not intelligence and wisdom. It leads to knowledge. I told you that AI will go for finding the optimal solution, whereas ML will go for only solution, whether it is optimal or no. Okay, so you just simply think the term machine learning was first introduced by Arthur Samuel in 1959. It is said as a subset of AI that is mainly concerned with the development of algorithms which allow a computer to learn from data and past experiences on their own. It enables a machine to automatically learn from data, improve performance from experiences, and predict things without being explicitly programmed. In machine learning, classification refers to a predictive modeling problem where class level is predicted for given example input data. It is being used for various tasks. Okay, image recognition, speech recognition, email filtering, password protecting, recommendation system, and many more. So these all are the block diagram of working on machine learning: input data, training, so learn data and build a model, new data. What this is what test data, where you are going to an output. So what is this? It is simply it uses data to features, detect various patterns in given data. It can learn from past data, improve automatic data. What is data-driven technology? Actually, data-driven technology means company makes strategic decision. Company makes what? Strategic decision based on what? Data analysis and interpretations. It makes strategic decision to keep happy to their customer or consumer. Okay, it is much similar to data mining as it also deals with a huge amount of data. Okay, fine. So what is the need for machine learning? The need for machine learning is, you know that the need for machine learning is increasing day by day. The reason behind the need for machine learning is that it is capable of doing tasks that are too complex for a person to implement directly. As a human, we have some limitations as we cannot access the huge amount of data manually. So for this, we need some computer systems, and here comes the machine learning to make things easy for us. We can train the machine learning algorithm by providing them a huge amount of data and let them explore the data, construct the model, and predict the required output automatically. The performance of machine learning algorithm depends on the amount of data, and it can also determine by the cost function. Okay, so the importance of machine learning can be easily understood by its use cases. Currently, machine learning is used in self-driving car, and we know that. Okay, so actually, you have read in AI types of AI. What is AI? Types of AI: ANI, AGI, and ASI. Artificial narrow intelligence, artificial uh, three terms was there. What we have studied: artificial narrow intelligence, artificial general intelligence, artificial super intelligence. What is the philosophy of AI? Can a machine think and behave like humans do? So what is ANI? You have already, some experts have discussed it in the lecture. What is ANI? Artificial intelligence. This is just used for one means this is just for domain specific. This is just for one problem. Just like you have heard Alexa. We told Alexa, I want to listen this song. We get it. So this is the popular example of what ANI. Suppose AGI, so artificial general intelligence. This means which kind of intelligence we are having. In the same way, uh, what we have to design some system, some machine. This is what ASI. So we are working. We are only in SI phase and AGI phase. Sorry. Then artificial super intelligence, ASI. ASI means what the person who means more intelligent human beings. Brain should be 4 times. Means this is beyond the human thinking. What is called ASI, but we are just in working in AGI. So okay, so right now looking at the key points which allow some important machine learning. Okay, so right now you already know there are 3 classification systems: supervised, unsupervised, reinforcement. Okay, the above 3 types of learning may be classified based on the presence or absence of a trainer. Then so we have already seen what is supervised, what is unsupervised, what is reinforcement. So I no need to go in so much there. I have shown you here 2 algorithm, what is NeoBase and J48 gravity decision tree, and both are what supervised. Why we already seen that in supervised training and testing is there, means there will be a trainer. Okay, so you may see a supervised learning means the correct target output values are known for each input, but unsupervised learning help of the trainer. Supervised here learning is performed with the help of a trainer. The block diagram, what is block diagram? Input, okay, method, actual output. This is actual output. Desired output, error generator, error signals. Okay, so what is going to be D minus 1? When it will be means minimum, then it is going to train the thing. Okay, so unsupervised, there is no any trainer. Suppose consider the example learning process tadpole. It learns by itself. A child will learn to swim by itself. It is not taught by its mother. This is the diagram. Okay, so its learning process is independent and is not supervised by a teacher. Okay. Similarly, in ANN, the input vectors of similar type are grouped without the use of training data to see how a member of each group look or to which group members belong. In the training process, the network receives the input patterns and organizes these patterns to form cluster. So, okay, the supervised and supervised learning methods are the most popular learning compared to reinforcement. Reinforcement learning is just similar to supervised. Here, error signal generator will be there, but not D minus 5. Okay, there is no D minus 5. So, it has to just what sense. Yeah, only little bit error are there and it is going to run. So here critic information is available, not the jet information. Okay, so 50% only information will be available in case of reinforcement learning. So about three types of learning is means these all are the rule, and what using three types of learning: heavy and competitive, stochastic. Okay, so you may see here network learning algorithm: supervised, reinforcement, unsupervised. Supervised what? Stochastic, error correction, gradient testing. Unsupervised, heavy and competitive. So list mean square. Okay, so you have seen here. So what is soft computing? Soft computing deals with approximate model and gives solution to a what complex problem. So gives soft computing deals with approximate model and gives solution to a complex problem. Soft computing uses a combination of genetic algorithm, neural network, fuzzy logic. So what is the main goal? The main goal of soft computing is to develop intelligent machines provide solution to real world problems which are not model or too difficult to model mathematically. Its aim is to exploit the tolerance for approximation, uncertainty, imprecision, and partial truth in order to achieve plausible monetization. So, what is approximation? By approximation, means the model features are similar to real one. The model features are similar to real one, but not the same. What is uncertainty? Uncertainty means the people are not sure that the model, the feature of the model are same as that of the entity. And then imprecision. Imprecision means the model feature are not the same as that of the real, but close to them. Okay, so soft computing builds, I told you already. Soft computing, why actually we are using machine learning, deep learning, and okay. So these all are soft computing. There is two terms: soft computing and hard computing. So main questions for any algorithm, for any data set, why we go only for soft computing, not choosing hard computing? So reasons you may see here. Soft computing is generally used due to the following reason. Soft computing can deal with ambiguous and noisy data, whereas hard computing requires exactitude. Suppose we are having the ambiguous and noisy data, soft computing work in it, but hard computing is not going to work on it. Soft computing allows parallel computation, means it is much faster, whereas hard computing is sequential, means it is what slow. Okay, it is going to take time. Soft computing can use multi-value, whereas hard computing uses two value. So multi-value means you know that this is multi-value and this is only 0 1, but this is not only 0 1. Okay, so soft computing incorporate stochastically, where hard computing is deterministic. Okay, so you know that deterministic means stochastically means probability based, means random variable. Hard computing means yeah, the output is going to be same. Okay, soft computing can yield approximate answer, whereas hard computing produces precise answer. So what is the main goal of soft computing application in diagnosis? Accurate detection, early diagnosis, risk factor identification. So data mining. Okay, because I have shown you J4A. So what is this? Data mining. It is not just a technology. It is the analysis step of knowledge discovery in databases. So most important and popular data mining techniques are classification, regression, clustering, association rule, prediction, equation pattern. And these techniques are used for variety of applications: healthcare, supply chain, quant finance, marketing, social network analysis, test mining. Okay, so here is two terms: data mining, predictive tasks and static tasks. So what is predictive task? Predictive task is simply predictive. Okay, so okay, so 1 minute. Somebody is, I think, trying. Actually, option is not coming, no? My screen is, I need to once again. So this option. So I was discussing data mining. Okay, predictive. I was telling predictive task. I was discussing You just see this. Predictive task means to find the value of feature using the value of other feature. These all are the examples. Descriptive task, the patterns that are human interpretable. Okay, so these all are the explanations. So feature selections, I told you, also known as attribute selection or variable selection or variable subset selection. These all are the same name. It is a process of selecting important feature or base subset of feature or relevant feature by removing the redundant and irrelevant feature or noisy or insignificant feature. It will save the resources while improving their accuracy and accuracy. So how I am just giving in layman language, I want to just tell you what is the role of feature selection. Suppose you are suffering from what? Diabetes. Okay, and if physicians or dietologists write you go for 6 tests. So okay, you will go for 6 tests. So our and some doctor physicians is going to write you only 2 tests. Okay, but output is what? Same. Means you are going to be diagnosed the same. Yeah. So what is the drawback for 6 tests? Time is going to be taken more. Money is going to be taken more. Why? Because you will go in lab. Many people will be involved for 6 days. Chemicals is going to be required more. So of course, more price is going to be given. But whereas into time is also going to be reduced, as well as we have to what also pay less money. In the same way in computer, if more data is there, so we require high processor, high memory, everything we require. You may not execute the task, you may not perform the task, but you will have less number of, and a time is also going to be conducted more. But if you have less number of data, of course, it is going to be compute fast, as well as in less means version of processor and memory, we may do our task. So this is the role of feature selection. With the help of feature selection, we can save storage capacity, computation time, computation cost, increases classification rate. I told you how to perform all these. So, show how much time? Okay. So actually, we have to also take care for validity. So this data set I have shown you. Okay. Shown you experiment how to partition this, and these two data set over there. Okay. So okay, to this level, if you are having any doubt, please ask me, because I am going to share you one quiz, and we have to just 10-15 minutes to take care for validity session. Okay, and okay, show me. Please just ask me questions if you are having what I have shown, what I have discussed, because I have to take care for validity also. By 4:40, I am just going to share you one quiz. Okay, and you have to just complete in within 15 minutes, and by 4:40 validity session is going to be started. What I have taught you in this portion, if you are having any doubt, you may ask from me. I have told you how to partition the data set, how you have to perform classification, feature selection in Vika. So I think it is going to help you a lot. Those who are having different background, if they are feeling, I am not good in coding and all that. Yeah, is there anyone who is curious to ask? Or I am going to say, okay, so I am going to share you queues. Okay, just complete, and suppose what is the time right now? 4:13. 4:13. So 4:15 to 4:30 your queues time, and after 4:30 10-minute break. By 4:40 your validity session is going to be started. Okay, so thank you, and I'm going to stop the recording and sharing you what queues, and complete it. Thereafter we are going to start validity. So thank you everyone. Thank you.